Every single year, construction workers around the world install over 34 billion square feet of drywall, enough to cover the entire state of Rhode Island twice over. This seemingly simple building material forms the interior walls of virtually every home, office, and commercial building constructed in the modern world. Yet most people have no idea how these flat white panels get manufactured. Here's what's absolutely incredible. Drywall production represents one of the fastest-moving manufacturing processes on Earth, with production lines creating continuous sheets of finished wall panels at speeds exceeding 8 feet per minute, 24 hours per day. So how does ordinary gypsum rock get transformed into the smooth wall surfaces that surround us every day? How do millions of tons of raw mineral get processed into the building material that quite literally shapes our indoor world? Today we're breaking down the extraordinary process inside one of the world's largest drywall manufacturing facilities, where over 1 million square feet of drywall gets produced every single day from raw gypsum that started as ancient seafloor deposits millions of years ago. Make sure to subscribe as we explore the incredible engineering behind creating the material that forms the foundation of modern interior construction. The journey begins in massive gypsum quarries that extract the raw mineral from geological deposits formed when ancient seas evaporated, leaving behind layers of calcium sulfate that crystallized into the pure gypsum rock essential for drywall production. These quarries operate like precisely choreographed industrial symphonies, with enormous excavation equipment working around the clock to extract gypsum that meets the strict purity requirements needed for high-quality building materials. Modern gypsum mining operations use controlled blasting techniques that fracture rock formations without creating excessive fines that would be difficult to process efficiently. Explosive charges get precisely positioned and timed to create optimal rock fragmentation while minimizing waste and environmental impact. The blasting operations require careful coordination with weather conditions and seismic monitoring to ensure safe and efficient extraction. Transportation of raw gypsum from quarries to manufacturing facilities involves specialized heavy haul trucks capable of carrying over 100 tons per load across distances that can exceed 50 miles. These massive vehicles operate on dedicated haul roads designed to handle the enormous weights while minimizing dust generation that could affect surrounding communities and environmental systems. At the manufacturing facility, incoming gypsum undergoes quality testing that verifies chemical composition, moisture content, and physical properties that affect final drywall performance. Laboratory analysis checks for impurities that could affect setting times, strength development, or appearance of finished drywall panels. Advanced testing equipment can analyze gypsum composition in minutes, enabling real-time quality control decisions. Primary crushing operations reduce quarried gypsum from blocks weighing several tons down to pieces smaller than baseballs, using massive jaw crushers that can process over 1,000 tons of rock per hour. These crushers use specially hardened steel components that resist the abrasive wear that gypsum creates, while maintaining precise gap settings that control final particle size distribution. Secondary crushing further reduces gypsum particle size using impact crushers that create the optimal size distribution for efficient calcination processing. The crushing process requires careful dust control systems that capture airborne particles while maintaining worker safety and environmental compliance. Advanced screening systems separate crushed gypsum into different size fractions that optimize downstream processing efficiency. Storage and handling systems maintain massive inventories of crushed gypsum in climate-controlled environments that prevent moisture absorption or contamination that could affect product quality. Automated conveyor systems move materials throughout the facility while maintaining complete traceability from quarry source through final product shipping, enabling quality control programs that can identify and address any processing issues. The crushed gypsum now enters calcination processes that transform raw calcium sulfate dihydrate into calcium sulfate hemihydrate through carefully controlled heating that drives off precisely 3/4 of the chemically bound water molecules. This process, called calcining, creates the plaster of Paris that forms the core of all drywall products, while requiring temperature control measured in single degrees to achieve optimal setting characteristics. Rotary kilns, measuring over 150 feet in length and 12 feet in diameter, slowly rotate while heating gypsum to temperatures between 290 and 320 degrees Fahrenheit. The kilns operate continuously, with gypsum entering at one end and calcined plaster emerging at the other, After carefully controlled residence times that ensure complete but not excessive dehydration, temperature monitoring systems track kiln conditions at dozens of locations, while automated fuel injection systems maintain optimal heating profiles that achieve uniform calcination without overheating that could create dead-burned plaster unsuitable for drywall applications. The calcination process requires precise control because variations in heating can dramatically affect the setting, time, and strength of finished drywall. Natural gas combustion systems provide the heat energy for calcination, while advanced emission control systems minimize environmental impact through pollution prevention and waste heat recovery. The combustion systems use computerized controls that optimize fuel efficiency while maintaining the precise temperature profiles needed for consistent plaster quality. The calcined plaster undergoes grinding operations that reduce particle size to optimize mixing characteristics and setting performance in final drywall production. Ball mills containing thousands of steel grinding balls reduce plaster to powder fineness while maintaining temperature control that prevents rehydration during the grinding process. Quality control testing of calcined plaster involves setting time measurements, strength testing, and chemical analysis that verify the material meets specifications for consistency, performance, and regulatory compliance. Advanced testing protocols can predict how plaster will perform in actual drywall production, enabling process adjustments that maintain product quality. The drywall forming process begins with precise mixing operations that combine calcined plaster with water and specialized additives to create a slurry with properties carefully engineered for optimal flow, setting time, and final strength characteristics. Advanced mixing systems can process over 20 tons of plaster per minute while maintaining consistency that ensures uniform drywall properties across millions of square feet of daily production. Water quality control is absolutely critical because even small amounts of dissolved minerals or organic compounds can dramatically affect plaster setting characteristics and final drywall performance. Water treatment systems remove impurities while maintaining precise temperature control because water temperature affects mixing, viscosity, and working time available for forming operations. Additive systems inject carefully measured quantities of starch, foam agents, glass fiber, and other materials that enhance drywall properties, including weight reduction, fire resistance, moisture resistance, and ease of installation. These additives must be dispersed uniformly throughout the plaster slurry using high-speed mixing equipment that creates homogeneous mixtures without introducing air bubbles that would weaken the final product. The continuous forming process creates drywall panels through a remarkable manufacturing system where liquid plaster slurry gets sandwiched between moving sheets of recycled paper that form the face and back surfaces of finished drywall. This process happens at incredible speeds, with the entire forming line moving at over 8 feet per minute while maintaining precise thickness control across sheet widths exceeding 12 feet. Paper handling systems manage enormous rolls of recycled paper weighing over 2 tons each, feeding continuous sheets through forming equipment while maintaining precise tension control that prevents wrinkles or tears that would create defective drywall. The paper feeding systems can switch between rolls without stopping production, enabling continuous operation 24 hours per day. The forming head represents the heart of drywall manufacturing, where liquid plaster slurry gets deposited onto moving paper in precisely controlled thicknesses, ranging from 1/4 inch to over 1 inch, depending on product specifications. Advanced flow control systems distribute slurry uniformly across the entire sheet width while maintaining consistent thickness that varies by less than 1/32 of an inch. Edge forming systems create the tapered edges that enable seamless joints between drywall panels during installation. These systems use specially shaped rollers and guides that compress and shape panel edges while the plaster is still soft, creating the precise edge profiles that drywall installers depend on for professional-appearing wall finishes. The setting process begins immediately after forming as chemical reactions between plaster and water create crystal structures that transform liquid slurry into solid gypsum panels. This hydration process generates heat that must be carefully managed to prevent thermal stresses while ensuring complete crystal formation throughout the panel thickness. Temperature monitoring systems track the setting process using infrared sensors that detect heat generation patterns across the moving drywall sheets. Advanced control systems can adjust water temperature, additive levels, and line speed based on real-time temperature measurements that indicate setting progress and final strength development. Conveyor systems transport freshly formed drywall through carefully controlled environments that optimize setting conditions while protecting panels from disturbance during the critical hardening period. These conveyors extend over half a mile in length, providing residence time that enables complete setting before cutting operations begin. The continuous drywall sheet moves through cutting stations that use precision knife systems to create individual panels of standard dimensions, including 4 foot by 8 foot, 4 foot by 12 foot, and specialty sizes for specific construction applications. High-speed cutting equipment can slice through moving drywall sheets without stopping production while maintaining edge quality suitable for construction use. Automatic cutting systems use computer-controlled positioning that can adjust panel lengths in real time based on production orders while maintaining cutting accuracy within 1/8 of an inch. The cutting blades require frequent replacement and precision sharpening to maintain clean cuts that prevent edge damage during shipping and installation. Edge finishing operations clean up cut edges and remove any irregularities that could affect panel appearance or installation performance. Automated edge treatment systems can process thousands of panels per hour while maintaining consistent edge quality across all production runs. Bundle formation systems stack cut drywall panels into packages sized for efficient shipping and handling at construction sites. Automated stacking equipment positions panels with precision while inserting protective materials that prevent damage during transportation. The bundling process must accommodate different panel sizes and weights, while creating stable packages that resist shifting during shipping. Quality control throughout the forming process involves continuous monitoring of thickness, moisture content, edge quality, and setting characteristics using automated measurement systems that can detect variations invisible to human inspection. Advanced scanning systems check every square foot of production for defects, while statistical process control identifies trends before they affect product quality. Moisture content testing verifies that panels achieve optimal dryness levels for shipping and installation while preventing over-drying that could cause brittleness or cracking. Automated moisture sensors provide real-time feedback that enables process adjustments to maintain consistent moisture levels across all production. Strength testing subjects sample panels to loading tests that verify structural performance meets building code requirements for wall and ceiling applications. Flexural strength testing ensures that panels can withstand installation stresses, while impact testing verifies resistance to damage during construction activities. The continuous production system operates with incredible efficiency, producing over 40,000 square feet of drywall per hour, while maintaining quality standards that ensure consistent performance across billions of square feet of annual production. Advanced automation enables this remarkable productivity while minimizing waste and environmental impact throughout the manufacturing process. The drying process represents the final transformation that removes excess moisture from formed drywall panels while achieving the strength and dimensional stability required for construction applications. Massive kiln dryers measuring over 400 feet in length create carefully controlled environments where heated air circulation removes moisture without causing warping, cracking, or other dimensional changes that would make panels unsuitable for installation. Temperature control during drying requires precision that balances moisture removal rates against thermal stresses that could damage panels or create dimensional instabilities. Multi-zone heating systems maintain different temperature profiles throughout the dryer length, with temperatures ranging from 150 degrees Fahrenheit at the entrance to over 400 degrees at peak drying zones. Air circulation systems move enormous volumes of heated air through drying chambers while maintaining uniform conditions across the entire panel width and throughout the dryer length. Advanced fans capable of moving over 1 million cubic feet of air per minute create the airflow patterns needed for efficient moisture removal while preventing hot spots that could cause panel damage. Humidity control systems monitor moisture levels throughout the drying process, while making automatic adjustments that optimize drying rates without overdrying that could cause brittleness or surface defects. Sophisticated control systems track moisture content in real time, enabling precise process control that achieves target moisture levels within narrow tolerance ranges. The drying process typically requires between 45 minutes and 2 hours, depending on panel thickness and moisture content, with computer-controlled residence time management, ensuring that each panel receives optimal drying treatment. Advanced tracking systems monitor individual panel progress through the dryer while coordinating with upstream forming operations to maintain continuous production flow. Energy recovery systems capture waste heat from drying operations to preheat incoming air and reduce overall energy consumption by over 30% compared to conventional drying systems. Heat exchangers transfer thermal energy from exhaust air to incoming fresh air, while emission control systems minimize environmental impact from the drying process. Final inspection operations examine dried panels for surface defects, dimensional accuracy, and moisture content using automated systems that can detect quality issues invisible to human inspection. High-resolution cameras scan every square foot of panel surface, while laser measurement systems verify thickness, uniformity, and edge straightness to tolerances measured in fractions of an inch. Edge inspection systems check cut edges for chips, tears, or irregularities that could affect installation performance, while automated sorting systems divert any defective panels for recycling back into the production process. Quality standards require that edge defects larger than 1/4 inch result in panel rejection and reprocessing. Packaging operations prepare finished drywall panels for shipping using automated systems that create protective wrapping while maintaining package integrity during transportation and storage. Specialized wrapping materials protect panel surfaces from moisture and mechanical damage while enabling easy unwrapping at construction sites. Strapping and banding systems secure drywall bundles using high-strength plastic or steel strapping that can withstand the stresses of transportation and material handling equipment. The strapping process must distribute loads evenly across panel bundles while providing secure attachment points for lifting equipment used during shipping and installation. Warehouse operations manage massive inventories of finished drywall using automated storage and retrieval systems that can locate and move specific product types and sizes based on customer orders. Advanced inventory management systems track product location, manufacturing date, and quality test results while coordinating with shipping schedules to ensure timely delivery. Quality assurance programs ensure that finished drywall meets all performance specifications through comprehensive testing protocols that verify strength, fire resistance, moisture resistance, and dimensional stability. Sample panels from each production run undergo laboratory testing that simulates decades of in-service conditions through accelerated aging and environmental exposure tests. Fire resistance testing subjects drywall samples to standardized fire exposure conditions that verify compliance with building code requirements for fire-rated wall assemblies. These tests measure temperature transmission, structural integrity, and flame spread characteristics that determine appropriate applications for different drywall types and thicknesses. Environmental impact assessment reveals that modern drywall manufacturing achieves remarkable material efficiency through recycling programs that capture and reuse virtually all production waste while minimizing energy consumption and emissions. Paper-facing materials contain high percentages of recycled content, while gypsum recycling programs recover waste material from construction and demolition activities. The facility operates comprehensive recycling programs that process waste drywall from construction sites, renovation projects, and manufacturing operations. Advanced separation systems remove paper facing and metal fasteners while recovering clean gypsum that gets processed back into new drywall production, achieving material recycling rates exceeding 90%. Sustainability initiatives include water recycling systems that treat and reuse process water while achieving near zero discharge of contaminated water. Energy efficiency programs utilize waste heat recovery, advanced process controls, and renewable energy sources to minimize environmental impact while maintaining high production volumes. Transportation logistics coordinates shipping operations that deliver drywall to construction sites using specialized trucks equipped with handling equipment designed for efficient unloading and placement. Load planning systems optimize truck utilization while ensuring that fragile drywall panels receive proper protection during transportation across distances that can exceed hundreds of miles. Innovation continues advancing drywall technology through development of enhanced formulations that provide improved fire resistance, mold resistance, sound dampening, and installation characteristics. Advanced manufacturing techniques enable production of specialty products, including lightweight panels, high-strength panels, and panels with integrated vapor barriers or thermal insulation properties. This remarkable manufacturing facility produces over 360 million square feet of drywall annually, enough to construct interior walls for over 60,000 average homes while supporting construction projects that provide housing and commercial space for millions of people. The precision manufacturing and material efficiency demonstrate how advanced industrial processes can create essential building materials while minimizing environmental impact. Research and development efforts continuously explore new applications and improved manufacturing techniques that promise to enhance drywall performance while reducing production costs and environmental impact. Future drywall products may incorporate smart materials, improved recycling characteristics, and enhanced performance properties that expand applications beyond traditional wall construction. And there you have it, the absolutely incredible process of transforming ancient gypsum deposits into 34 billion square feet of drywall that forms the interior walls of our modern world. The precision, efficiency, and environmental responsibility of drywall manufacturing showcases how advanced industrial processes can create the essential materials that literally shape our daily living and working environments. What other construction materials would you like us to explore? Drop a comment below and let us know what you think. And don't forget to like, share, and subscribe to keep exploring more fascinating industrial journeys with us.